So let's calculate the middle Riemann sum and compare it with the Riemann integral. And again, we're going to use f of x equals x squared on the interval -2 to 3 with 5 subintervals. So we said that the middle Riemann sum is equal to the summation I equals 1 to 5 f sub x sub I star times 1, which we can suppress. So that's going to be equal to f of x sub 1 star plus f of x sub 2 star plus f of x sub 3 star plus f of x sub 4 star plus f of x sub 5 star. And each of these terms that we've written here correspond to the area of the rectangle on a particular subinterval. So x sub 1 star was minus 1.5. X sub 2 star was minus 0.5. X sub 3 star was 0.5. X sub 4 star was 1.5. And x sub 5 star was 2.5. Now remember, f of x equals x squared, so I can write each one of these as minus 1.5 squared plus minus 0.5 squared, and so on. And if you multiply that out, you're going to get 11.25. So this middle Riemann sum is equal to 11.25. As we said in a previous video, the Riemann integral is simply the limit of the Riemann sum. So this 11.25 is an approximation to the full Riemann integral -2 to 3 x squared dx. Now, if we do this one, we're going to get x cubed over 3. We're going to go away from -2 to 3, which is 3 cubed over 3, minus -2 cubed over 3, which when you're said and done is simply 11.6 repeating. So this value right here is, if you like, an approximation of the Riemann integral. Okay. All right. How much error is this approximation to the full Riemann integral? Well, what we simply do here is we subtract the middle Riemann sum. Okay. We're going to subtract that from the actual interval. So what we're going to do is we're going to take this value right here, which is 11.6, and subtract 11.6 repeating, subtract 11.25, and we get a value which is equal to 4.416 repeating. So this, if you like, is the error in the approximation. This error right here is sometimes referred to as the approximation error. Or sometimes referred to as the true error. The reason it's called the true error is because we're comparing the approximation to the true value for the thing that we're trying to approximate. How can we make this approximation better? Well, we can improve our approximation by choosing a larger n. Okay. What this means is exactly what we showed in a previous video, that the integral for minus 2 to 3 of x squared dx is equal to the limit as n approaches infinity of the summation I equals 1 to n f of x sub I star times delta sub xi. So again, what this equation means is that you can make the approximation on the right-hand side as close to the integral by simply making n sufficiently large.